Hello, this is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is June 30th, 2016. In this video lecture, we will be covering the true power output of a two-stroke gasoline piston engine. In a two-stroke gasoline piston engine, there are two piston strokes to complete one duty cycle. The stroke cycles have nothing to do with the number of cylinders, but they denote the number of piston stroke displacements to complete one duty cycle. So on a two-stroke gasoline piston engine, there is a downstroke and an upstroke to complete one duty cycle, and there is exactly one revolution of the crankshaft for every one power stroke. The way this works is that the downstroke, you will have the power, air fuel intake, and exhaust events happening on the downstroke, and then you'll have the compression and ignition events happening on the upstroke. So how this works is that there is an exhaust port. Here's the cylinder. And on the bottom of the cylinder, there's an exhaust port, which is usually blocked off by the piston. And then on the top of the air fuel entry into the cylinder, there's something called a reed valve. It's like a plate valve that only allows air and fuel in one way, but when the piston starts to compress the air and fuel, the compression pressure pushes up on that plate valve and blocks off any flow outward. So it's called a reed valve opposed to a poppet valve, like on a four-stroke piston engine, where you have like a camshaft pushing up the valve, and then the valve comes down on the valve seat to seal it. Well, on a two-stroke gasoline piston engine, there is something called a reed valve, and it's just a plate that is designed to allow air and fuel to go one direction, inward, but when the piston comes up under compression, it doesn't allow the air-fuel charge to go the other direction. So that's basically how you contain the fuel-air charge based off piston position. So when the two-stroke gasoline piston engine is started up, it's of course connected to the crankshaft, right, on the crankcase. Inside of that crankcase, the harmonic dampener acts like an air-fuel pump to draw the air-fuel in from the carburation and intake manifold area down into the crankcase. The fuel will lubricate the engine in a two-stroke gasoline piston engine, because the fuel on the two-stroke gasoline engine, the gasoline, it has to be mixed with a two-stroke oil at the ratio of 4 ounces two-stroke oil per every 128 ounces of gasoline, which is equal to 1 U.S. gallon. So 128 to 32, or 128 to 4, that equals 32 to 1. That's what they mean by 32 to 1 two-stroke gasoline mixture. That's what they mean. So now this gasoline has been treated, 1 gallon has been treated with 4 ounces of two-stroke oil. So this changes the lubrication properties of the gasoline, allowing it to lubricate the engine first before that fuel-air charge is pushed by the crankshaft dampener as like an air-fuel pump. It's pushed out and it's pushed into the cylinder through a scavenged cross-flow air-fuel induction system, which then goes into that plate valve, reed valve. So also assisted by the piston coming down. So the piston, along with the crankshaft dampener, they act like air-fuel pump to pull in the fuel-air charge. After the fuel lubricates the crankshaft and the piston rings, then it goes into the reed valve, and then the piston, as it comes down the downstroke, it also creates more vacuum. It draws the air-fuel charge in, and then when it comes to the bottom of the piston stroke, on initial startup, there might be a tad bit of fuel air charge leak out of the exhaust, a little bit, but not enough to be significant, just for a split second. And then when the piston comes up, it actually closes that exhaust port off, and then the air fuel charge goes into the compression, and then right before the piston goes to top dead center, the ignition event occurs, and then when the piston goes to after top dead center, maximum combustion gas pressure absorbs on the piston head. Pressure times area equals dynamic force. The piston absorbs that force, transmits it to the connecting rod. Connecting rod transmits it to the crank pin, and it converts that brake mean effective pressure into brake horsepower and torque to the crankshaft. So that's how the two-stroke piston engine works. Now we can go over the engine math to calculate the true power. Now, whenever you look at a piston engine horsepower rating, you cannot use the HP rating because that is the indicated horsepower. That is the theoretical total power going on in the engine, including the power lost to keep the engine running, the friction horsepower, added to the usable power left at the crankshaft, the brake horsepower. So when you add the friction horsepower, the power lost to keep the engine running, plus the power available that's usable, the brake horsepower, when you add those two together, you get the indicated horsepower, the HP. So HP doesn't tell you anything about the power you can use. It only tells you the total power going on in the engine. So you have to focus on the BHP, the brake horsepower. And so the way to do that is you have to take the brake mean effective pressure that builds up on the cylinder during every power stroke. You got to multiply that times the piston stroke length in feet, so inches stroke divided by 12, times the piston head area in square inches, which is pi r squared, the bore diameter divided by 2 squared times 3.14 pi, times the number of power strokes per minute. So on a two-stroke piston engine, the power strokes per minute are equal to the RPM because there is 1 revolution per power stroke. So you use the maximum foot-pounds torque rating at a given RPM, which should be on the specifications of the two-stroke gasoline piston engine, and you use that RPM for the power strokes per minute. Then you multiply those 4 times the number of cylinders, and let's say it's 1 cylinder, like on a chainsaw. Then you take those 5 values, multiplied out, and you divide it into 33,000 foot-pounds per minute, the number of foot-pounds per minute to 1 horsepower. You got to use foot-pounds per minute because it's in terms of RPM, not revolutions per second, but revolutions per minute. 550 foot-pounds per second is 1 horsepower, times 60 seconds is 33,000 foot-pounds per minute. So now you got the brake mean effective pressure times the piston stroke length in feet, times the piston head area in square inches, times the number of power strokes, times the number of cylinders, multiplied out, divided into 33,000. Now, when you're dealing with a two-stroke piston engine, you have to take the foot-pounds torque rating, divide that by the cubic inches displacement of the engine, which is equal to the cc's times 0.061. cc's times 0.061. That will convert cc's into cubic inches. So the foot-pounds torque rating divided into the cubic inch displacement times 75.4. When you multiply those out, that will mathematically allow you to calculate the brake mean effective pressure in pounds per square inch on the two-stroke piston engine. So once you calculate that BMEP, then you multiply it times the piston stroke length, times the piston head area, piston stroke length in feet, piston head area in square inches, times the number of power strokes per minute, times the number of cylinders, then you divide it into 33,000. That will allow you to get the brake horsepower at the maximum foot-pounds torque rating at that given RPM. You need to always have an RPM tied to a horsepower and foot-pounds torque rating, although it doesn't have any value. So that's how you accurately measure the brake horsepower in a two-stroke gasoline piston engine. If you're just dealing with the total horsepower, which includes the power lost to keep the engine running, then you're kind of being misled on what that engine can do. So since the two-stroke gasoline piston engine operates at maximum RPM all the time, the faster a two-stroke gasoline piston engine operates, the cooler it will run, the more efficient it will run, because the fuel is used to lubricate the engine. So at higher RPM, there's more lubrication, and also at higher RPM, there's more airflow going through the cylinder. So everything runs efficiently and at a lower temperature when at higher RPM. That's why when you operate a two-stroke gasoline piston engine, like on a chainsaw or on a string trimmer, you're supposed to operate it at maximum full throttle. You never want to operate it at a low RPM, because then the fuel mixture will lean out, you'll get thermal runaway, you will not get enough lubrication to the engine, and you will not get enough airflow to cool the cylinder. So the two-stroke gasoline piston engine not only operates most efficiently at maximum RPM, but in order to get the rated foot-pounds torque, you need to operate it at maximum RPM. Because there also is not that much pressure coming on the piston head on a two-stroke gasoline piston engine, because the compression ratio is purposely created a lot lower on the gasoline two-stroke piston engine, because it's designed to get its maximum torque through the RPM and not through the BMEP. If you go to two-stroke diesel, that's a whole different ballgame. The engine block is designed for high pressure, unlike the gasoline. So only with a gasoline two-stroke piston engine, it's designed to be run at high RPM continuously with a lower compression ratio and lower BMEP on the cylinder head, but it makes up for that lower BMEP by higher RPM. So in the most basic form of brake horsepower, the formula is foot-pounds torque times RPM times 6.28. Those three values then divided into 33,000. That's the less accurate but easier way to calculate the brake horsepower. But if you were to have a lower foot-pounds torque because of lower BMEP on the piston and a higher RPM, that would be the same as having a lower RPM and higher torque, or lower torque, higher RPM. Mathematically, it's the same amount of brake horsepower. So the two-stroke piston engine gets its torque rating by RPM, but the four-stroke gasoline piston engine, it has a much higher BMEP per power stroke that it doesn't need the RPM to get its rated torque. So those are some of the differences and similarities between the two and the four-stroke gasoline piston engine. But to get the BMEP on the two-stroke gasoline piston engine, you need to use the ratio between the foot-pounds torque and cubic inch displacement. But at this time, instead of 150.8, you multiply it times 75.4, which is exactly half of the pressure coefficient of a four-stroke gasoline piston engine. So that's the dynamics and the true power concept and calculation methods for the two-stroke gasoline piston engine. In terms of brake thermal efficiency, the two-stroke gasoline piston is the same as the four-stroke gasoline piston engine. 1/3 is lost to heat the engine block. 1/3 is lost in the form of waste heat out of the exhaust. And then 1/3 is left to drive the piston. The two-stroke oil is made out of a compound called naphtha, and this causes the straight gasoline to have a lubricating quality. And some might argue that you're going to get a little bit more energy with the naphtha in there, but that's not true, because even if there was an effect with more energy with the naphtha oil additive, most of its energy qualities are lost in the form of lubrication, and also there isn't the compression to actually fire that oil. So, of course, you're going to get more pollution out of the exhaust, a lot of smokiness, because a lot of that oil is just purged out of the system with the fuel air charge. So they're more pollutant, of course, but there's still going to be 20,000 BTU per pound heat energy content in two-stroke gasoline, just as there is in straight four-stroke gasoline. That oil additive is negligible because, first off, there isn't the compression ratio in the two-stroke gasoline engine to fire that oil, and secondly, that oiling, lubricating property is going to be spent in the form of lubrication through the system, so its energy effects are negated. And lastly, of course, for every 1 BTU over 1 minute time you release in the form of heat from burning fuel, you will get 17.6 watts of mechanical power, whereas there is 746 watts of power to 1 horsepower. So these are the basic power dynamics and how to calculate the true power of a two-stroke gasoline piston engine. Thank you for watching this video, and look in my YouTube video library for the two-stroke diesel piston engine true power output and the four-stroke diesel piston true power output. Thanks for watching this video, and have a great day.